Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
The asteroid belt, the cosmic archive of the solar system. The asteroid belt exists as a dynamic and ancient region in our solar system, a cosmic repository of remnants from the epoch when the planets were first taking shape. In its seemingly tranquil expanse between Mars and Jupiter, it harbors a multitude of rocky bodies that offer a window into the processes of planetary formation, collisional evolution, and the gradual sculpting of a solar system in its infancy. Long before humanity possessed the instruments to observe these enigmatic objects up close, early astronomers marveled at the scattered points of light that defied simple categorization, each discovery hinting at a far richer and more complex history than previously imagined. The initial sightings and cataloging of these bodies, beginning with the serendipitous identification of the largest member by Giuseppe Piazzi, marked the start of a long journey toward understanding the intricate dance of gravity, motion, and time that has kept these remnants in a delicate state of suspension over billions of years. This early period of discovery was driven by a blend of telescopic ingenuity and theoretical insight, as scholars began to speculate on the forces that prevented these clumps of matter from coalescing into a full-fledged planet. The gravitational influence of a nearby giant, whose relentless tug had long been suspected and later confirmed, imposed constraints on the growth of these bodies, effectively arresting the process of accretion and leaving behind a scattered field of primordial material. Over time, as observational techniques improved, it became apparent that these bodies were not merely inert debris but active participants in a cosmic narrative that involved violent collisions, gradual grinding through mutual impacts, and complex orbital resonances. It was a narrative that unfolded over eons and challenged prevailing ideas about the isolation of planetary systems from the turbulent processes that govern their evolution. In parallel with these early theoretical advances, the advent of space exploration ushered in a new era of discovery that transformed the asteroid belt from a distant curiosity into a laboratory for studying the early solar system. Missions dispatched to venture into this region were designed with an audacity that matched the ambition of their scientific objectives. One mission in particular, which employed an innovative ion propulsion system to slowly but persistently alter its orbit, managed to insert itself into a prolonged study of two of the belt's most significant bodies. This mission not only orbited a dwarf planet but also circled a once molten world whose surface bore the scars of ancient volcanic activity and later collisional reshaping. The data returned from this pioneering journey revealed details of surface composition, thermal evolution, and even subtle signs of volatile compounds, clues that pointed to the presence of water ice hidden beneath dark, ancient crusts. Such findings not only challenged previous assumptions about the chemical uniformity of early solar system materials but also provided tangible evidence that the seeds of life might have been sown in the very dust from which our planet later emerged. Before these orbiters delved into prolonged observations, earlier spacecraft had already performed daring flybys of solitary asteroids, skimming past them at breathtaking speeds to capture fleeting snapshots of their rugged terrains. These encounters, occurring during gravity-assist maneuvers on trajectories that would eventually carry their host spacecraft to more distant targets, provided the first up-close glimpses of these worlds. The images returned by these missions revealed surfaces pockmarked by craters and fractures, each impact a silent record of a tumultuous past marked by countless collisions. The discovery of small natural satellites accompanying some of these bodies further underscored the complexity of interactions that can occur even among relatively diminutive objects in the solar system. Such unexpected findings stirred the scientific community, sparking debates and driving forward theories regarding the mechanisms of binary formation and the dynamic balance between gravitational forces and collisional disruption. Beyond the breathtaking images and detailed chemical analyses, the data gathered by these early missions also carried implications for our broader understanding of planetary defense and the future of space exploration. The meticulous mapping of orbital paths, the identification of potential hazards, and the characterization of surface properties served not only as a testament to human ingenuity but also as a guide for future endeavors aimed at deflecting objects that might one day threaten our home planet. The lessons gleaned from these missions, in terms of both technological innovation and scientific discovery, have laid a foundation upon which subsequent studies continue to build. The interplay between theory and observation in the asteroid belt has proven to be a fertile ground for testing ideas about the stability of orbits, the evolution of surface features under constant bombardment, and the processes that gradually erode or even rejuvenate these ancient bodies. At a deeper level, the asteroid belt has served as a natural chronicle of the solar system's evolution, preserving within its myriad objects the signatures of processes that took place when our cosmic neighborhood was in a far more volatile state. The interplay of thermal histories, magnetic field interactions, and the subsequent cooling and solidification of once molten interiors is recorded in subtle variations in surface texture and mineral composition. Through painstaking analysis, scientists have been able to reconstruct aspects of this history, linking fragments of rock found on Earth to their larger counterparts in the belt. Each mission that has ventured into this region has contributed a new chapter to this ongoing narrative, unraveling mysteries that extend from the ancient past to implications for future exploration. The continuous flow of data from these ventures has underscored not only the scientific richness of the asteroid belt but also the diverse challenges encountered in navigating its domain. The low-gravity environment, coupled with the presence of small, irregularly shaped objects, has demanded a level of precision and adaptability in spacecraft design that was unprecedented. These missions have had to contend with the uncertainties of a region where minor gravitational nudges can lead to significant changes in trajectory, and where the margins for error in both navigation and data collection are exceedingly slim. Despite these challenges, each successful mission has added to an ever-growing repository of knowledge that informs both the history of our solar system and the potential pathways for future interplanetary travel. In the quiet vastness of interplanetary space, the asteroid belt continues to unveil layers of complexity that extend far beyond its visible contours, drawing researchers into a realm where minute variations in physical structure and composition speak of processes operating on scales both microscopic and cosmic. Investigations that probe the subtle interplay between collisional dynamics and thermal evolution have revealed that these bodies are not monolithic relics but rather intricate assemblages that have undergone profound internal transformation. Advanced spectroscopic techniques, refined through decades of laboratory calibration, have enabled scientists to decipher the mineralogical signatures imprinted on asteroid surfaces by ancient heating events and subsequent exposure to the harsh environment of space. Through these spectral fingerprints, researchers have discerned evidence of localized melting, shock-induced metamorphism, and even episodes of aqueous alteration that hint at the transient presence of water in environments once thought to be utterly barren. These revelations have spurred a rethinking of the early solar system, where the diversity of chemical and physical conditions within the belt appears to have fostered a wide spectrum of evolutionary pathways, each recorded in the layered, often fragmented, bodies that now orbit in silent testimony to epochs long past. The progression of our understanding has been marked by missions that, rather than simply cataloging surfaces, have delved into the nuanced details of an asteroid's internal architecture. One such expedition charted a course that brought a spacecraft into an extended period of close observation over a cluster of bodies, employing innovative sensor arrays that measured thermal emissions, surface roughness, and even subtle variations in gravitational fields. The data acquired by these instruments allowed scientists to infer the presence of loosely bound aggregates, often described as gravitationally reassembled rubble piles, whose internal cohesion, or lack thereof, offers clues about the cumulative effects of countless micro-collisions and the persistent influence of solar radiation forces over immense spans of time. This intricate mosaic of internal structures has provided a natural laboratory for testing theoretical models of material strength under low-gravity conditions, models that have, in turn, refined our broader understanding of how small bodies in the solar system respond to both gentle nudges and violent impacts. The interplay between empirical observation and simulation in these studies has led to new insights into the processes that govern the fragmentation and reaccumulation of material, revealing that the balance between destruction and creation is as delicate as it is relentless. Simultaneously, the art of remote sensing has evolved into a precise tool for mapping the heterogeneous landscapes that characterize asteroid surfaces. Instruments aboard spacecraft have captured images of terrains where fine dust coexists with exposed bedrock, where the interplay of shadow and light uncovers ancient craters and hidden grooves that record the passage of time. Detailed analysis of these features, performed in tandem with experimental studies on Earth, has begun to unravel the mechanisms by which surface materials migrate, settle, and even coalesce into transient structures under the influence of microgravity. The surface regolith of these bodies, once thought to be a homogeneous covering, is now understood as a dynamic medium shaped by processes such as impact gardening and electrostatic levitation, phenomena that continuously modify the external appearance and thermal behavior of an asteroid. The emerging picture is one of constant flux, where even seemingly static objects harbor layers of history that are rewritten with each encounter with a stray particle or a fleeting gust of solar wind. In a parallel vein, the analytical methodologies applied to light reflected from these distant rocks have grown increasingly sophisticated. Researchers have managed to extract information about the distribution of complex organic compounds and hydrated minerals from the faintest spectral signals, constructing maps that reveal how these vital ingredients are dispersed across different regions of the belt. The discovery of such materials, often concentrated in areas that suggest past exposure to transient warming events, has profound implications for theories regarding the delivery of prebiotic molecules to the early Earth. These findings suggest that the processes of chemical synthesis in the primordial solar system may have been far more widespread than once envisioned, with the asteroid belt serving as both a reservoir and a crucible for the compounds that underpin the chemistry of life. This chemical heterogeneity, when considered alongside the intricate physical textures observed on asteroid surfaces, paints a picture of a region that is as much a record of cosmic chemistry as it is a dynamic environment governed by relentless mechanical processes. The continuous refinement of computational models, spurred by the high-fidelity data returned from recent missions, has further illuminated the complex interactions that define the belt's evolution. Simulations that integrate the cumulative effects of countless minor collisions, the thermal forces exerted by solar radiation, and the subtle influences of gravitational interactions have provided a framework within which the long-term stability of these objects can be assessed. The results of these models have not only corroborated observational evidence but have also predicted phenomena that are only now coming into focus as sensor technology improves. These theoretical constructs offer a glimpse into the future, suggesting that the delicate equilibrium maintained within the belt may eventually be perturbed by external forces or internal instabilities, leading to shifts that could alter the very architecture of this ancient region. It is a reminder that even in a place where change appears imperceptibly slow, the underlying forces are ceaselessly at work, weaving a narrative that spans billions of years. Amid these scientific endeavors, practical considerations have begun to take shape that point toward the future exploitation of the belt's resources. The detailed characterizations of thermal properties, material composition, and mechanical integrity have informed early-stage concepts for harnessing extraterrestrial resources. Although the prospect remains in its nascent stages, the notion of extracting water, rare metals, and other vital materials from these ancient bodies has captured the imagination of both scientific and entrepreneurial communities. This evolving vision of in-space resource utilization rests on the premise that the same data which deepens our understanding of the belt's history might one day underpin a new era of interplanetary industry, a future in which the asteroid belt transforms from a distant repository of ancient matter into a vibrant node in a network of off-world commerce and exploration. The relentless pursuit of knowledge in this frontier has fostered an environment in which international collaboration and interdisciplinary inquiry flourish. Scientists and engineers, drawing on insights from astronomy, geology, physics, and chemistry, have joined forces to tackle the many mysteries that the belt continues to present. Through coordinated efforts that span continents and cultures, the community has forged an understanding that transcends the limitations of any single discipline or mission. The synthesis of observational data, laboratory experimentation, and theoretical modeling has created a rich tapestry of knowledge that not only elucidates the past but also charts potential paths for future exploration. In this spirit of collaborative discovery, the asteroid belt emerges not as a static relic of a bygone era but as an active participant in the ongoing story of the solar system, its secrets waiting to be deciphered by the next generation of explorers and scientists. NASA's Dawn mission marked a revolutionary chapter in exploring the asteroid belt. Launched on September 27, 2007, Dawn set its sights on two of the belt's largest bodies, arriving at the protoplanet Vesta in July 2011 and later transitioning to orbit the dwarf planet Ceres in March 2015. Through its multi-year investigation, concluding in November 2018, it delivered unprecedented insights into the composition, geology, and evolutionary history of these ancient worlds, fundamentally reshaping our understanding of how planetary building blocks survived the early solar system's tumult. NASA's Psyche mission, which launched in October 2023, is well into its journey toward the metallic asteroid 16 Psyche. Currently in transit, the spacecraft is executing precision maneuvers to ensure it arrives on schedule in early 2026. Believed to be the exposed core of an early protoplanet, 16 Psyche offers an unprecedented opportunity to explore the inner workings of planetary formation and differentiation. As the mission continues its voyage, it is set to investigate the asteroid's magnetic field, detailed composition, and internal structure with state-of-the-art instruments. The insights gained from these studies are expected to not only illuminate the processes that forged metal-rich planetary cores but also pave the way for future considerations in space resource utilization, deepening our understanding of both our solar system's past and its potential future. Each new insight gleaned from the belt's diverse array of bodies reinforces the notion that the region is a crucible of cosmic evolution, where processes both subtle and violent interplay to shape the destiny of these ancient wanderers. The cumulative narrative that has emerged from decades of meticulous research is one of continual transformation, a saga written in the language of physics and chemistry, etched into the very surfaces of these rocks by the inexorable passage of time. It is a story that invites us to look deeper into the nature of change and continuity, to appreciate the delicate balance between forces that both erode and create, and to recognize that the seemingly silent expanse of the asteroid belt is, in reality, a vibrant archive of the solar system's most profound mysteries.